Is now a good time to start?
Yeah, we are able to hear.
Yes, sir. Can you hear me, sir?
Yeah.
Yeah.
Sure.
Okay. Hello, everyone. Good afternoon. Namaste. Today we are here for an interesting session on introduction to wet spinning of polymers. This session will be taken by Dr. Johnny Hunter, sir. Dr. Johnny Hunter is R&D manager at FET. He brings an enormous wealth of academic credentials to the department, including a master's in medical and biological chemistry and a PhD in sustainable chemistry. This solid academic background is complemented by over 10 years R&D experience in industry, including FMCG and in particular medical devices, which encompasses wound care, the medical device manufacturing process and regulatory environment. He has spent the last 18 months leading the team at FET and has significantly grown the team in the size and technical knowledge. We welcome you, sir. Uh, now, over to you, sir.
Wonderful. Thank you very much. I will, if that's okay, I'll take over the screen and start sharing a short presentation. Assuming this all looks. Do it this way around. I'm just having some slight troubles on the technical side of things, getting it to share my screen. There, lovely. I just want to check you can all see this presentation slide.
Yes, sir. It is visible, sir.
Fantastic. So let's get started then. So you'll notice that it's not just me in the room. So first of all, thank you for the introduction and the very kind invite to come give this presentation. Obviously you have myself and you give me a lovely introduction, and with me I have one of my team members, Charlotte, who will be talking you through a certain specific section of the presentation as well. So Charlotte is a research assistant who's been with FET for about 4 or 5 months now.
4 months, yeah.
And so she'll be talking a little bit around some practical sides around wet spinning. So, as this is an introduction to wet spinning, I thought it was worth beginning with an introduction to FET. So, for those who are not familiar, I'll let you understand what we do and how we have worked in wet spinning for a number of years. Then move through what is meant by wet spinning, why we wet spin, and what do we actually mean by wet spinning? Because there's a lot of terms used in the literature and in lots of articles that claim to be wet spinning but are subsects of that. At that point, Charlotte's going to talk through some practical parts about wet spinning alginate fibres, and then I'm going to finish off with some real world case studies of when wet spinning has been used by our customers. Clearly it's going to be redacted, so you won't know what customers those are, but I still think it's useful to understand some of the pitfalls that our customers have fallen into and some successful examples of where wet spinning has been moved into industrial production. Just to finish off as well, we'll finish off with some questions at the end. So if you can keep all of your questions to the very end of the presentation, that'd be much appreciated. So FET stands for Fibre Extrusion Technology. We are 25 years old as a company and based in the UK, in the north of England, quite close to Leeds, as you can see on the map on the left-hand side. Now, FET primarily designs, develops and manufactures extrusion equipment into lots of technical textile industries, whether that's for clothing, for medical device products, for aerospace components, a wide range of materials or equipment made. And we also have a world-leading R&D facility, which is the facility that I run. In this facility, we have examples of all the equipment we sell for customers. So you can test drive or do a trial on that equipment prior to purchasing the equipment. Basically de-risking a project, making it much more viable, and also so you know when you have your own equipment, you can transfer the technology very easily. We've been in the building for about 2 years, so it's still quite new and shiny. Now, FET works across a range of technologies. I am going to mainly focus on wet spinning today, but I will talk briefly around the others. So feel free to get in contact if any of these other pieces of technology are of interest to you. So melt spinning is a key area for FET. Having equipment that is small scale and R&D pilot scale is really important to us, and the niche where we work. For reference, pilot and R&D means different things to different people. So I would highlight that we usually work in a scale of production of around 1 to 10 kilos per hour. That might be very big to some people, but equally it'll be very small for those who are familiar with commodity textiles, where small scale might mean ton per hour. The reason why we do that is we're looking primarily at a high value, low volume products, but we work across quite a wide range of technologies. Because we're trying to be, our equipment is for R&D uses, we make sure that it's as flexible and as changeable as it can be. So the equipment you'll see on the screen here has been able to process over 120 different polymers in the last 10 years, and that number is ever growing. We've made a range of different products for lots of different industries. Bottom left is our melt spinning, our multi-filament system. Through this, we have extruder going through a screw, metering pump into a die, and then a spin draw wine cabinet to achieve the level of fully drawn yarn that you would want at the end of a multi-filament process. And on the top right, we have our monofilament line, which is very similar and can make either single filament mono products or what we call multi-monofilament products as well, to maximize that throughput in a system. After melt spinning, the next area that I'll highlight is FET's non-woven capabilities. So we've developed 2 systems to make both melt blown and spun bond non-wovens. Really, these are based on very similar technologies to the melt and mono spinning equipment you saw previously, and they can handle the same materials. So that's a key differentiation point for FET's equipment, is that the same polymers that we put through our mono and multi-filament, whether that's high viscosity, low viscosity, we can extrude those and make them into non-wovens in the same or very similar process. So we've had a lot of success, particularly with melt blown. So we can take very challenging polymers like PEEK or biodegradable polymers like PHAs or PGA, and being able to make those into non-wovens in a single step. So finally, and probably most importantly for today's talk, I'm going to talk through the wet spinning technology that we offer. This falls into 2 forms, either low viscosity or high viscosity. So low viscosity on the left and high viscosity on the right. You should be able to see that well, by the end of this lecture, you should see that the downstream process is very similar in both, via a washing and drawing system. The main difference between the 2 is the spin dope vessel, where we've had to design the high viscosity system to be able to handle materials like lyocell spin dope, as an example, which requires a much higher viscosity to extrude those fibers. But that's a starting point about what FET does, and I will move us swiftly on to what is wet spinning and why you would want to do it. So melt spinning is probably the technology that most people are familiar with. This is where you take a polymer, heat it up, and push it through a die to form filaments, either mono or multi. It's relatively straightforward in a high throughput process. Now, you can't always do that. So some polymers are unable to be melt spun. So oftentimes people then move to wet spinning as an approach. So some reasons why you would do that is that the degradation point, the point at which the polymer breaks down, is lower than the melting temperature. The next is that the polymer, even when it's molten, may not flow. And that's particularly true with polymers that have really high molecular weight. And finally, there's a subset of fibers that require a chemical reaction to produce a fiber. So really, those are some of the main reasons. There are others, but I think that's enough for today. And the two things I would highlight, particularly between melt spinning and wet spinning, the real differences are that melt spinning is primarily a physical process. You are heating up and pushing a polymer through an extrusion system. It's a highly efficient process. Typically, you can get into 95 plus polymer to product yields, so really highly efficient processes. Whereas wet spinning, as I said previously, is typically a chemical process. It can be much less materially efficient, but the yarns that you produce at the end have unique properties that you are not able to achieve by any other route so far developed. So, as we're talking about chemistry, we need to make sure that we do it safely and carefully, and you keep the correct PPE on. So we need to get our lab coats on, because some of the chemicals you'll be working with are pretty terrifying. Now, the reason why I've included a picture of Steve Irwin in the center is that we can learn a lot from his example, even in this picture. So you can see he's holding a crocodile or an alligator, I'm not sure, which is a very dangerous beast. But when you handle it carefully and respectfully and know what you're doing, you can care and look after these things in a very safe fashion. In much the same way as the chemicals you'll be potentially working with when you're wet spinning. So around the edge of the picture, I have a range of chemicals that you may come into contact with whilst wet spinning and are commonly used. The reason I'm talking about this first is safety is always of great importance, because you don't want to, a lot of these chemistries will be able to take your arm off just in the same way a crocodile or a lion would be able to, just as quickly. So, for example, viscose in the top right-hand corner. I don't know whether you can see my mouse, but here we are. Top right-hand corner requires the use of carbon disulfide to be able to break down the cellulosic pulp. That is a flammable, toxic, and irritant product, which is pretty horrible, and I wouldn't want to get anywhere near it if I had the option not to. Next, for those who come across aramids, for making things like Kevlar, they often use highly concentrated sulfuric acid. Now, you'll note on there that it's highly corrosive, so you need to make sure the equipment is safe and able to handle those corrosive materials. But equally, I would highlight that it's a fuming acid, which means you not only have to deal with the acid that's in the bath or coagulation solution, but equally you need to be prepared to deal with the vapors that come off there, which are also highly corrosive. Now, on top of that, going to the top left-hand side, PBO, for instance, uses phosphoric acid, similarly highly corrosive. And finally, I'll touch on spandex in a moment, which uses dimethyl formide as a solvent, which is flammable, harmful, and irritant. It's particularly dangerous is that to unborn children. So those are things that you need to be aware of going into this process, because they're commonly found in wet spinning technologies. So, what is wet spinning? Is another question. And I've often read a lot around what wet spinning is. And as an introductory point, I thought it's worth to highlight that regularly all of these terms that you'll see in this collection are often called wet spinning or forms of wet spinning. So moving from left to right, we have, if I can find the mouse again, there we are. We have gel spinning. So gel spinning, at each one of these I'll come through in a moment, but gel spinning is in a little bit more detail, but gel spinning is used primarily to make something called an ultra high molecular weight yarn. This is a good example of that is a Spectra product made by a company called Honeywell. And that yarn is incredibly strong and light. So it's often used in construction equipment to be able to lift very heavy objects. So the image below is a boat being lifted with that material. In reality, if it was using steel ropes, then the steel ropes would break under their own weight. So the only real option is to use something like an ultra high molecular weight yarn. Next, we have a term called dry jet wet spinning. Again, like I said before, I'll come to more detailed description of each of these later. But in dry jet wet spinning, you can make things like lyocell, viscose products, aramids, and I hope I don't need to tell anyone, but aramids are often used in things like Kevlar, so body armor, and those sorts of materials. Next, we have dry spinning, which can be classed as a form of wet spinning, even though it has its own differences. And a prime example of that is spandex, which had its often used in sportswear and had made a huge cultural impact in the 80s, changing fashion at the time. And finally, we have wet spinning within the wet spinning family, which may be surprising, but things like proteins, chitosan, alginate fibers, PAN can be made via wet spinning which is often made into carbon fiber for those who want to go down that route. So let's walk through each one of these so you can get a bit more familiar with wet spinning and the terms that are often encompass products of wet spinning. I'll try and highlight the differences and some of the interesting points through these. So, gel spinning. In this instance, you would take a powder of a polymer, in this case ultra-high-molecular polyethylene, and dissolve it in, say, mineral oil or other oil-based materials. And the loading in this, as you'll see I've highlighted in the top right-hand corner, is about 5% weight per volume. So for every kilo of yarn or spin dope you're producing, only 5% of that is the polymer you want. The other 95% is oil. So you can see already that you will have to process a lot more material to get to the same yields of kilos of yarn that you want at the very end than in melt spinning. And this is true throughout all the wet spinning processes that I'll go through, but I will highlight those as we move forward. So polymer dissolved in mineral oil through a metering pump into a spinneret. This allows you to make a single or multiple filament or single filament. And in this instance, you're going through what's called a quench or an extraction bath. This solidifies the polymer and then starts removing that mineral oil. Now, mineral oil is a highly non-polar solvent. So you need something that's similarly non-polar to remove that mineral oil. A good example that is often used in literature is dichloromethane. I'd highlight that dichloromethane, whilst being non-flammable, is incredibly carcinogenic. So again, these are some of the materials you may be coming in contact with. From there, once the mineral has been removed, the yarn is then taken through an oven to dry off any of the dichloromethane, which will boil at around 35-40 degrees Celsius. Now, as we're in the UK, we don't often hit 35-40 degrees Celsius, but as this is an international lecture, I would highlight that some of those people on the call may regularly hit 35-40 degrees Celsius. So these are things to consider whilst exploring this technology. So from the oven, you can then produce a yarn, and that yarn, as I said before, has a very, very high strength to density ratio. So you may be able to produce a 40 denier yarn with a 1 dpf per filament profile and a tenacity of over 30-35 grams per denier tenacity. So very strong and very light yarn. So that's gel spinning. We'll now move on to dry jet wet spinning. So there are some subtle differences that I'll try to highlight, and the majority of those are in the spinning end of things. So in this instance, this is how lyocell processes work. So lyocell is where you take a cellulosic material, put it into an aqueous or water-based solution with NMMO, which is the reagent required to dissolve that product. Now, you're spinning the dope at around 90 degrees, and then there's what we call an air gap, so which is where the dry jet part comes from. There's an air gap between the spinneret and the coagulation solution, which is significant, like I said, different from the gel spinning, in that gel spinning uses an extraction and quench bath. This uses a coagulation bath, where there is a chemical reaction that takes place. And you'll notice here that this NMMO is around 20% in the coagulation bath, progressing that spinning of the lyocell fibers all the way from quite high levels of NMMO down to lower levels, and eventually washing all of the NMMO out into the aqueous water that's used during the washing process. Now, I would highlight that you're potentially making a fiber here from a renewable source, cellulose, from wood pulp. However, This technology was first developed by a company called Lenzing, and they've spent a long time being able to recover and recycle the NMMO that is used to try and make it as sustainable as possible. Primarily because the NMMO is very expensive, but equally, and something to be cautious of if you were to explore this technology, is that NMMO can, if not controlled carefully, undergo an autocatalytic exothermic reaction and basically explode. So again, I'm trying to show you the process behind this, but also highlight to you the caution one must take when approaching any sort of wet spinning. So we've now done gel and dry jet. Dry spinning is similarly related. In this instance, with spandex, you're taking a polymer and dissolving it into a solvent. This solution is then extruded through a spinneret, and there's then hot air, or I would recommend more of a hot inert gas, something like nitrogen or argon, is blown over those filaments to evaporate the solvent. Now, in this instance, the solvent is dimethyl formide. It's got a boiling point of around 180 degrees, so you need to have a gas that is that temperature or slightly higher to be able to evaporate that solvent very rapidly. And you're also getting an output from the evaporation chamber of hot, flammable, toxic gas dissolved in a inert gas. So some people want to recover that and reuse it again via a trap, for instance, a cold trap. But equally, this comes with its own health and safety precautionary requirements. Now, spandex has a very high elasticity level, giving it its unique properties and requirements. So, finally, within the wet spinning family is what I would classify as true wet spinning. So, in this instance, you've got, again, a spin dope. In the example I'm using here, we've got chitosan, which is made from shellfish and those sorts of materials, dissolved in water with a small amount of acetic acid, so an aqueous acidic solution. The spin dope is not particularly hazardous. However, the coagulation solution in this instance is sodium hydroxide solution, which can be anywhere from 0.1 to 1 molar concentration, which is around a similar concentration to soap. So it's not going to be incredibly dangerous, but it's something to be aware of, that if you regularly putting your hands in and out of that solution, that you may want to wear some protective equipment. So, as I was saying, the main difference in this instance is that the spinneret is actually submerged within the coagulation solution. That can either be submerged fully, as you can see in the image here, or submerged horizontally into the solution, so the spinneret base is just touching the solution. So we've produced equipment to do both routes. Now, once you've coagulated and the chemical reaction has taken place to form those filaments, you want to collect the filaments, wash them in a bath, dry them, and then go through a take-up winder or roller, as it says on here. So this gives you another unique offering via chitosan, is that you can produce fibers that have hemostatic properties, so they can clot blood really, really well. So this is something that can be used in emergency situations. So if someone's been had an accident or been stabbed or shot or something along those lines, then these sorts of materials are really useful to stop the blood from flowing and allowing that patient to be taken from the site of the accident or injury and taken to hospital. So that briefly brings me to the end of my section. And I'm going to pass you over to Charlotte, who's going to talk you through some of the practical aspects of alginate spinning. So over to you, Charlotte.
Okay. So I'm just going to start with what actually are alginates. So they are salts of alginic acid, and this is found in the cell walls of brown algae. So, for example, you can see in the picture on the right, giant kelp, and also in some bacteria. It is a polysaccharide, so that means it is a long chain of sugar molecules. The two sugar molecules that make up alginates are beta-D-mannaronic acid and alpha-L-glucuronic acid. Now, these chemical names, for the moment, I'll just call them M and G units, as it's a lot easier to deal with them in that way. And then, so once you have your alginic acid, when it forms a salt, for example, with sodium, it will become sodium alginate. Now, this is the one that's mostly found in seaweed, as it is soluble in water. So this is what you would use to form your dope that goes in your vessel, which can undergo an ion exchange to form calcium alginate, which is insoluble in water, and this would form your fibers. So just to go a bit more into the chemistry of alginates, as you can see on the left of the screen, at the top, you've got your G units, and then in the middle, you've got your M units. So the M units, when they line up together, make a very linear, flat chain, whereas the G units, when they line up together, make a chain that looks a bit like it's got a cup shape in it. So then at the bottom, if you've got a mixture of M and G, this makes a chain with kinks in. So on the right, if you can see the egg box model that's there, if you have two chains that are made up of more of the G units, they can fit together quite nicely to make a shape similar to an egg box. And then in the middle, you can fit an ion. So with the sodium alginate, that ion is monodentate, so will only bind to one of the polymer chains. Whereas when that changes for a calcium ion, this is bidentate, which means that it can bind to two different chains at the same time. And this forms crosslinks between two different polymer chains. This is what gives the alginate its strength and stability. This also means that the monomer units that make up your polymer have a very big impact on your final product. So things like the length of the chains, so how long or how many monomer units you have, the more of those you have, so the higher the molecular weight, the stronger your final fiber is going to be. But then this also means that your spin dope is more viscous. Another thing that will affect the viscosity is the polydispersity. So this is the distribution of the polymer chain lengths. So how many different lengths of chains that you have, as well as the number of M and G units. So alginate from different sources will have different amounts of M and G in them. And alginates with more G units can do more cross-linking and will be stronger and make a more viscous solution. So this means you can have two samples of alginate that are from different sources, and even if you make them to the same concentrations in the same way, they can have very different properties and greatly affect your final product. What can you use the alginate for? So you may have more likely to come across it in things like the food industry. So as an encapsulating agent, it's used in things like bubble tea or boba tea, which makes the tasty little popping bubbles at the bottom of the drink. But more for what you would wet spin alginate into is the medical applications at the top. So things like wound dressing and tissue engineering. Because alginate is a biopolymer, it's also compatible with the human body. There's unlikely to be any adverse reactions, so you can implant it to help with growing tissue, which means it's quite safe to use for things like wound dressings. So when you're actually wet spinning an alginate, this is probably something you would start with if you're new to wet spinning, as the chemistry is fairly innocuous and relatively simple. So you have your vessel, which contains the sodium alginate dope. So you would dissolve your sodium alginate in water. This is normally anywhere between 3 and 10%, depending on how viscous you need your solution to be. Then you would extrude that through the spinner into the coagulation bath. This is made up of calcium chloride dissolved in water. This is basically salt water, so like you would find in the sea. It's normally about 1% calcium chloride to 99% water, so it's not very strong. However, I would still recommend caution. It can dry your hands out a lot and obviously will sting quite badly if you get this in your eyes, so goggles and gloves are recommended. So the calcium that's in the coagulation bath exchanges with the sodium in the dope to make your calcium alginate thread. This is washed in the water baths and then can go through several different drying processes, so the hot air zone and the oven, before finally going onto your winder at the end. Some of the challenges you might come across when you are wet spinning alginates. So first of all, as you can see, starting from the left, when you degas your solution. So mixing the sodium alginate into water can be a little bit tricky, as it can get quite viscous, so the solution can become very thick, and then this incorporates air bubbles from the mixing, and you don't want any air bubbles in your solution. So some of the ways to overcome this is you can remove the bubbles using an ultrasonic bath, or once your dope is inside the vessel, we can apply a vacuum to suck the air out and therefore the bubbles out of the sodium alginate solution. The reason that you need to get rid of the bubbles is if you extrude through a spinneret with the bubbles in the solution, the air gaps in the solution will cause the alginate to coagulate inside the spinneret head and block the spinneret. This can then cause your fiber to have much fewer filaments than it's supposed to, will increase the pressure in the spinneret, and will cause your final yarn to be a lot lower denier than you want it to be and have much lower tensile properties. So degassing is a very important step to take. Next, you need to consider the viscosity of the spin dope. So highly viscous solutions, as you can see, the holes in the spinneret are very small. So that is 100 holes in that spinneret. These are about 0.1 millimeter in diameter. Getting a very viscous solution could be, so not with alginates, but with cellulosic fibers, it can be up to 500,000 centipoise, which is similar to peanut butter, things like that. Don't want to go through such small holes. So you have to apply pressure inside the vessel in order to push the spin dope out through the spinneret. Now, when you have a more viscous or more concentrated solution, this can be helpful because it makes a very strong fiber at the end. However, in the opposite direction, if your viscosity is too low and your spin dope is too runny and not very concentrated, there'll be very little amounts of alginate that you're coagulating, and this can produce a very weak, thin fiber that is difficult, if not impossible, to process, and then doesn't have very good properties in the end. So as you can see in the left, in a sodium alginate solution is blue. Now, normally, without adding any colors, it is a sort of beige to yellow solution. The reason we would add a color in is because observing the fibers can be quite tricky. So in the picture that's third along, you can see the fiber as it's coming out of water over the guide. In air, very easy to see. However, once it's in the water, it's very tricky due to the refractive index being the same between the fiber and the water. So you can add a color, such as blue, to make the fiber easier to see, or we use a venturi, which is the tube you can see in the left of the picture. This means that you know exactly where the fiber is going to be coming out at the end of your coagulation bath, so you know where you will be collecting your fibers from. Finally, another challenge is drying the fibers. So when the alginate fibers are wet, they're fairly weak and don't have much strength. So you have to be quite careful with handling them to make sure they don't break. However, once they've dried, the properties will improve and they're a lot easier to handle. So drying is a very important step to take. We can do this in several ways. So in the picture on the right, you can see that it's been wrapped multiple times around ceramic godets that can be heated up to help dry the fibers. And in the previous picture, we had the hot air oven and the IR oven, so the infrared oven. So you can use a combination of these technologies to dry your fiber in order to be able to collect them at the end. So your final yarn, as you can see on the left, is the fully drawn yarn, is what you would like to end up with when you spin alginates. So this can then, for example, be processed further if you crimp it and then cut it up into staple fibers. This can then be further processed to make the hemostatic wound dressings that Johnny mentioned earlier.
Super, thank you for that, Charlotte. So, as I said at the beginning, we've talked our way through just a general introduction to wet spinning. Charlotte's given you a really lovely some tips for doing wet spinning practically. And now I'm going to work our way through 2 examples of real-world implementation of wet spinning. And the image you have on here is one slight tweak of equipment that we've had to be able to be ATEX rated and handle materials which are more challenging to work with. So, for example, to start off with, we'll talk about company X, who have been anonymized. They came to us because they were wanting to spin a sustainable textile. And like I said at the beginning, this is the sustainable part of this project, is that they're making a fiber from protein. In this instance, it was a recombinant silk to make a clothing line. Their spin dope had about a 5% protein concentration, and their coagulation solution was ethanol. So this worked really nicely for them when they were working at a very small scale, which a lot of our customers do. They'll come to us and say, we've worked on a benchtop scale, and we're now trying to move up to a larger scale and then fully commercialize the technology. So we can help from multiple different ends of the production spectrum. Now, I know this is quite wordy, but I will take you through it nice and gently. This particular customer had, as I said, a protein fiber that was around a 5% concentration. So if you follow the logic through with that, for every 5 kilos of protein fiber they wanted to make, then you needed to be able to process 100 kilos of spin dope. So it's quite a large step up from there. And finally, to be able to get into the ton scale to make clothes, so for every 5 tons of protein fiber they needed to be able to spin, they need to process over 100 tons of spin dope. So yeah, I guess you can imagine that took a very long time to do, to make not very much protein fiber. So that was quite a challenge for them, and also meant that their costs started to creep upwards. Secondly, looking at the coagulation solution, again, ethanol on a very small scale is relatively easy to handle. So for those who don't know, ethanol is alcohol that you can regularly find in alcoholic beverages. It's the same stuff. However, with high concentration of ethanol, it's very flammable, and therefore any of the equipment that came into contact was around the ethanol, or the fumes of ethanol, need to be what's called ATEX rated, so explosion proof, so it wouldn't spark and you then couldn't set off the ethanol and set it on fire. So unsurprisingly, that made the equipment slightly more expensive because it requires specific materials to achieve that ATEX rating. But then equally, the customer had decided or had experimented with their material and found that below a concentration of 50%, when the ethanol had extracted water to the extent that there was a 50-50 ethanol water concentration in the coagulation bath, it needed to be replaced. So the way that the customer had scaled this up, or what it meant for them, is that for every 30 kilos of spin dope, the coagulation solution needs to be replaced. So that was quite a challenge for us to design a way around doing that. It required a series of pumps, but we managed it. And then the other thing to keep in mind is that ethanol is not cheap. So you might be able to get it cheaper elsewhere, but I had a look yesterday at the price of ethanol from a company called Sigma Aldridge, who are a well-known chemical supplier, and their current price per kilo of high purity ethanol is around £90 or English pounds per kilo. So it regularly became very expensive. Now you can recover and reuse that ethanol via a process called distillation. That's very energy intensive. You're basically boiling the ethanol water mixture to recover the ethanol. And in the UK, I'm not sure about other countries, but at least in the UK, you need to have a license, which also includes extra cost and money. Now, unfortunately, the customer got to a point where they tried running the machine, that everything technically was working, but from a commercial sustainability point of view, the project wasn't viable. So unfortunately, this project didn't work. And so it was a environmentally sustainable project, but not a business sustainable project. So those are two things to keep in mind. Then I have another example, which is company Y. So this company was actually making an edible alginate fiber. So exactly the same material Charlotte was talking about earlier, but to make into a food-based product. The customer was actually using quite a little bit higher concentration than me and Charlotte have been talking about, so about 7%. So it's just slightly bit more viscous material, well within our scope to handle. It wasn't a problem on that front. And then the coagulation solution, again, as Charlotte touched on, is calcium chloride. So relatively cheap, relatively easy to handle, non-toxic material. So we didn't need any of the ATEX rating that I touched on previously. Now, so the equipment was cheaper and easier to use. The actual customer had quite a high water content within the final yarn product because it was going to be edible. They didn't want it too tough and strong because it was going to go into people's mouths. They really wanted it to just dissolve almost straight away. So that they found that they needed about 85-ish% water concentration in the final yarn. Therefore, it made their overall concentration yield throughput from spin dope to final product around 92%. So really quite high for a wet spinning product, mainly because it's mostly water. But then also you're getting into the realms that are similar to melt spinning. So this product, this company is still ongoing. The project's going really nicely, and it is a sustainable and project from an environmental point of view and also from a business point of view. So for those academics in the room, I would highlight that just because something is made from a renewable resource doesn't mean that that can automatically translate to a product that is going to make a massive commercial impact and work really, really nicely. So I'd think about those sort of things as soon as you can. So just to finish off, some general tips around wet spinning. Regularly use a low concentration of spin dope, so you may need to be having to process a lot of product to get the yarn quantities you want. Depending on which way you go, you may deal with very viscous spin dopes, which require a lot more processing than you may initially think you need, and that might require equipment which is needs to go to higher pressures and has higher strength motors to deal with more torque to allow you to mix and stir and extrude those high viscous dopes. I'm not going to go into as much detail as Charlotte did, but I would reiterate her point that degassing is massively important, and it can make or break how regularly you have to change that spinneret, how long your equipment can run for, and what productivity you can achieve. And finally, but by no means least, please be aware of the hazards you're going to deal with when you're doing these sorts of wet spinning processes, because some of the ones that I've highlighted today are pretty dangerous. Now, we've touched on some examples which are less so, and I would always recommend that if you're introducing yourself to wet spinning, you start at something easy and low hazard level, and then build your way up to something a bit more challenging, just to make sure you have all the safety procedures in place and the care is required that you take the care required that is necessary. So that's us. That's the full presentation I want to give you. We're just about on time, but I've included on here FET's website, so you can see that you can look up any of the information that you've seen today. You'll be able to find some of that on our website. you can get in contact with us regarding any equipment or trials you'd like to run on either wet spinning, melt blown, spun bonds, and the mono multi-filament lines. And I've also included myself and Charlotte's email addresses. So if you have any questions for us directly and want to know more about what we're talking about, please let us know. Okay, so I'm going to stop sharing now and hopefully open the floor to a couple of questions.
Your participant can unmute himself and ask the question directly.
Hi, this is Ravi Shankar. I wanted to ask you about the possibility of converting through wet spinning process a starch-based fibers. That means it is you use a starch and then convert it into a useful fiber.
Sorry, can you repeat the question? I didn't quite catch what you meant. You broke up a little bit.
I wanted to know if the wet spinning, can it be used for converting starch into a usable fiber?
So you're talking about starch, yes?
Yes.
So sugar. Okay. So in short, the answer should be yes, because starch is a sugar-based material. So if it's cellulosic-based starch or sugar-based, we've touched on some of the materials that Charlotte's touched on, which are polysaccharides, in the same way that starch is. I'm not familiar with anyone trying with starch, so you may need to then work on how you will coagulate it to form a filament. If you have if you can find a process that will work on that front, then that might be a route forward. But the equipment should be able to process that in the same way. The FET's equipment should be able to process that in the same way we do with chitosan or alginate. So that's how I would.
Thank you. So you develop only the machine, the chemistry, we have to give the chemistry. Is it right?
Correct. Yes. So we can help with the machine, but we'd always suggest that you guys are the owners of the chemistry.
Yeah.
Mainly because being a chemist myself, there's a huge array of things out there. We can make some potentially helpful suggestions, but ultimately this is your IP and your knowledge that you're bringing to the table, and then we can help you with produce the equipment to make it from small scale or what scale you're on now into a production scale or R&D pilot scale quantities.
That's great. So we'll write to you for how much you will be charges for the per hour basis or per day basis for taking some experiments.
Correct.
Right? Thank you. Thank you. Go ahead.
Okay, any other question from the participants?
So I have a questions related to the gel spinning. So first of all, it's a nice presentation, sir, and informative presentation. I have a question related to the gel spinning. Your gel spinning and dry spinning, because somewhere you have mentioned Spectra fiber is manufactured from the gel spinning and Dyneema is manufacturing from the wet spinning. So,
yes.
Sorry, dry spinning. So, or both are manufacturing from the gel spinning. So I have a doubt about that.
So I'll highlight why I've put them into those categories. So with Spectra, you're dissolving the ultra high yarn into a mineral oil and then extracting that using a non-polar solvent like dichloromethane. The Dyneema process is actually you are forming a gel, so you're quite right that it is a form of gel spinning, but typically you're not extracting the declin in that instance using a non-polar solvent. As far as I'm aware, and I'm happy to be wrong, and you may know more than I do, but from my understanding is that the Dyneema process uses declin, which is then evaporated rather than extracted. So it's more akin to dry spinning.
Is that dry spinning? Okay.
Yeah, so there may be also another category within this that would be like dry gel spinning. But I'm trying to when I put this presentation together, give a general overview, but there are crossovers and things that don't quite fall into the right categories, if that makes sense.
One more question, sir, related to the machine manufacturing, because I am
Yes.
looking for the gel spinning line. So
Yeah.
I have also raised a query on your website ki, what is the approximate budgetary for the gel spinning line. So I did not get reply response from your side, and so you are basically in the site only wet spinning and the dry spinning or those kind of process mentioned, but gel spinning line is not mentioned. So
Yeah. So there is a reason behind that. So if you've emailed the website already, then it'll probably be within our inbox. And if you email again, then I'll make sure we find that and go from there. Because sometimes emails can end up in a junk mail or something along those lines. It doesn't happen very regularly, but it can happen.
okay,
And
okay.
just to make you aware, we are towards the end of this year going to be launching a new offering that is directed entirely towards gel spinning of ultra high molecular weight yarn, because we found that currently the wet spinning equipment we have could be used for wet spinning for gel spinning of ultra high yarn, but it's not optimal. So we've spent a number of years optimizing that process, and then we're planning to launch this product towards the end of this year. So keep an eye on the website, and you'll see some new developments going on there regularly. Okay,
Okay. Thank you, sir.
you're quite welcome.
Uh, Good evening, sir. This is Dr. Kumar from NIT Jalandhar. So it's very nice presentation. I have very quick questions if you would like to answer that. So please.
Yeah.
So my question is related to how much minimum amount of polymer will be required. Suppose we are going for any dry spinning or gel spinning or any sorts of wet spinning or solution spinning. So how much polymer dope or to be required for that? See.
So our equipment is flexible. If you were to buy your own, then we can design the vessels from some around 5 liters to 100 liters. That's more than possible for us. We've also gone larger than that, but typically most people fall within the 5 to 100 liter range. The reason why we do it in that scale is to do with the concentration of the spin dope. So just using simple numbers, if you have a 5% concentration in a 100 liter vessel, then you can make, in theory, around a 5 kilo bobbin of yarn. And a lot of our customers then want to use that bobbin of yarn to then weave or braid or knit into a further product. And that's usually the limitation of the work, is that what's your downstream process? So we work with a lot of universities. We have wet spinning machines in a number of institutes around the world. And typically they find that around a 5 or a 10 liter vessel is fine for them. Because again, a 10 liter vessel may produce half a kilo of yarn, which is enough to make into a small swatch or square of material to do any sort of testing they want to do. So it's flexible on that front. But typically people aim small to start off with and then can always upgrade further down the line. So you may start with a 10 litre and then come back to us a year later and say, actually, I want a 100 litre vessel, and we can make it backwards compatible as well.
Oh, thank you, sir. Thank you for the information. It's very nice presentation and interaction with you.
Thank you.
So
I think I have time for one more question, if that's okay.
yeah, yes, sir. I think
Hi.
okay.
Hi, my name is Marcelo. I am from Chile. I work for Arauco, a pulp producer, dissolving pulp. And I wonder, regarding to dissolving pulp grades, are there more, let's say, some qualities that can produce better fiber in terms of the aeration or in terms of spinability? How you make trials, I think, for pulp companies also?
Yeah, so we do some trials for customers, depending on the chemistries that are used. And what we have, you'll see on the wall behind me, I have a wet spinning design of a machine. So we, on site here at FET in the UK, we have one of our low viscosity systems, and then we're working with a university in Europe to be able to offer trials on a high viscosity system. So those are two things we're hopefully, well, we can offer low viscosity already, And then high viscosity is something we're working on to be able to offer in the next month or so. Again, now on the website. Now, you were asking about how you can prepare the dope. I've seen lots of people working on lots of different things. For example, with cellulosic pulp, one of the areas that is of real interest in the academic world at the moment is moving away from either the viscose process, which uses carbon disulfide, the lyocell process, which uses NMMO, and I've seen a lot of people looking into ionic liquids, which are proposed to be a much more sustainable solution because they, in reality, they're really a form of a salt. They're a salt-based liquid. Now, the thing I would highlight is that the process to use an ionic liquid can be more sustainable. It may not always be, but it can be. However, the challenge that I foresee is that ionic liquids are regularly and being able to recover them after extrusion is very challenging to do so. It's highly energy intensive. So I've seen people moving into that route to make spin dopes more sustainable. And then there's a plethora of people working on lots of different things to try and make other spin dopes more sustainable as well. I hope that answers your question.
Sure. I think I will try to contact you after the meeting because it was a very interesting presentation to understand, because my interest is to understand what our customer can see, or an MMO producer, for example, if I gave you different pulp qualities.
Okay. So I think you're right. I think if you send me an email with that in, and then we can follow up afterwards. Okay?
Good, thanks.
Lovely. So I think I'm gonna have to leave it there because I need to. I've got to disappear to another one. But thank you very much.
Thank you, sir. Thank you,
You need
sir.
to wrap up on.
Yes, sir, please.
Lovely. Right. In which case, I'll thank you all for coming. And again, you have my contact details. So if you have more questions, please get in touch. Okay.